Okay, welcome again. Previously, the last lesson, this would have been number 4. We were looking at the molar gas volume, but just to recap of where we have come from, we have considered the simple elements, moles of compounds. We have come across of a number of particles in one mole of what simple compounds or simple elements. And then after that, I think we checked about something to do with percentage composition, and checking what makes up recap. Then on the last lesson, we looked at the molar gas volume, and this is where we said that if you take 1 mole of any gas, which of course it contains in the particular mass which changes depending on what the mass is. Although the mass changes for that 1 mole, there is something which does equivalence which does not change. First of all, the number of molecules in that gas will always remain constant, and or we also learned about the molar gas volume, the 24 dm cubed, or which is equivalent to 24,000 centimeter cubed. Uh, that 1 mole of any gas must occupy at room temperature and pressure. And using this one, we are able to calculate number of particles and do some calculations revolving around that particular element. Okay, so as I said, I think these lessons look at them from the very first lesson, go to the second one, go to the third one, go to the fourth one before you jump to the first that you are likely dependent on each other. If you fail to understand the first one, the second one becomes like easy. Each of them are like approximately 40, 50 minutes, which should be able to assist you in covering as much groundwork as possible. Remember also the way I said to read it, take the first lesson one. Just if you are beginning or if you have been having real troubles with this more concept stuff, just do 15 minutes. You can even do just the first 15 minutes. Leave it for the first day. That's day one, do 15 minutes. Day two, do from minute 1 to minute 30. Day three, do minute 1 to minute 45. And day four, in do minute 1 to minute 60 if it goes beyond 50. Day five, it the whole thing 1 to 60 again. Day 6 and 7, which happens to be like your Saturday and Sunday, don't do anything. Next week, if you feel comfortable with this, with the first lesson, go to the second lesson, repeating the same sequence. If you are not comfortable with one lesson, go back, try to the same thing the following week, and I'm certain that you'll be able to catch up or to grasp this concept. They are relatively easy, they are quite easy. But more important is to ensure that you go to your book once you get the concept to do exercises. That one cannot be overemphasized. Exercises, they are a must, and you may understand one moment, but if you don't practice, then you have yourself a problem. You are going to forget it before. Um, Now, after knowing how to do those calculations related to mole of element, simple element, mole of compound, molar gas volume, you realize most of the time is that we would be considering chemical reactions. And chemical reactions is essentially in the exam, whether it is the practical or it is the theory, is what you will find. So just to jump in there or to introduce this, consider this. We have our sodium. Of sodium, a small piece, you draw it or not to draw it, but drop it carefully in water. It spins around very fast, reacting with water to form sodium hydroxide solution. Okay, that's the formula of sodium hydroxide plus some hydrogen, which is a gas. Okay, sodium starts as a solid, and then water is a liquid. The solution which is formed is an aqueous solution, which means it's some kind of ions which are dissolved in water, or something which has been dissolved in water. And finally, we have the hydrogen evolves out as a gas. Okay, so those are the state symbols for that equation. Now, whenever we are writing the chemical equation, the next thing we must do is to make sure that it is balanced. And what is to balance is to make sure that whatever number of elements which are appearing on the left-hand side, they must also be appearing on the right-hand side. Okay, and this is what we are going to try and do simply here. So most of the time you find it is relatively hard to balance with the odd numbers. So because I can see there's how many sodium, one sodium on the left, one sodium on the right hand side. Okay, that seems balanced. Two hydrogen on the left hand side, then two hydrogen plus one, three hydrogen on the right hand side. That one now becomes a problem. We need to try to balance it. Let's first of all try to put in a two there. And then because we have changed, we start all the way at the beginning. One sodium there, one sodium on the left, two sodiums on the right hand side. So I need to make a two there so that I have two sodium on the left, two sodiums on the right. Okay. Then two hydrogens on the left and the hydrogen on the right. These two multiply separately, so it's two hydrogen. Those ones plus two, those are four. So I need to make those ones four. So I put a two there. This by this. Now I have four hydrogen on the left and four hydrogens on the right. Then what about oxygen? Two oxygens on the left and two oxygens on the right. So the equation is right now balanced. All right. So this one tells me that whenever I react sodium and water to form sodium hydroxide and water, the equation, whatever is on the left-hand side, those are reactants. Reactants, the items which we push in, they are reactants. And whatever is produced is the product. Okay? And this is what the equation shows you. And the plus sign over there says reacts with, it's like a sodium reacts with the water, and this one implies to form, or to give, or to form or to give sodium hydroxide and water and hydrogen gas. All right, that's the way you would read that particular chemical equation. So the chemical equation will show you the reactants, the products. It will show you the state symbols. It's this guy was solid, this other guy was liquid, the guy who was formed is an aqueous solution, and the other guy who was formed is the hydrogen gas, which was evolved. Okay, that's what we get from this chemical equation. When the equation has been balanced, there is one more very important item which it tells us, and it is the ratio in which these items are combining. And this we get them, and this is why getting the equation balanced very well is very important. This one tells me that it's like I have 2 moles of sodium reacting with 2 moles of water to produce 2 moles of sodium hydroxide, and to evolve, there is a one there which we are not writing, we don't write, but it's implied, 1 mole of hydrogen gas. Okay, so if I tell you that let me go with one complete quantity, 2 moles of sodium is like 1 mole of sodium is 23 grams. 1 mole of sodium is 23 grams. So 2 moles of sodium is something like 46 grams. Okay. If I start with 2 moles of sodium, which is 46 grams, I just multiplied this one by 2. By the way, Eh, I said 1 mole of sodium I know is equals to 23 grams. Remember lesson 1. What about 2 mole, which is implied here? Uh, how many grams is it? You'll find it becomes 46 grams. This is what we have been doing previously. Okay, so this one tells me that if I start with 46 grams of sodium, I must react it with 2 moles of water, and I must always get 2 moles of sodium hydroxide and 1 mole of oxygen. So if I needed to do a complete reaction and I have 46 grams of sodium, how much water molecule must I push in? What is the formula mass for the water molecule? H2O is so 2 hydrogen, 2H plus 1 O, oxygen. This is 1 oxygen. This is O. Please note this is an O, not a 0. So 2 hydrogen, 2 has a hydrogen has a mass of 1. 1 oxygen has a mass of 16. This one becomes 18. And therefore, if I'm looking at 2 moles, is 2 by 18, which implies 36 grams of sodium of sodium, and not of sodium but of water, mole of water, which is 36 grams, 2 moles of water. Then I must produce 2 moles of sodium hydroxide. What is the weight of 2 moles of sodium hydroxide? One sodium hydroxide is made up of 1 sodium, 23, that's sodium, and 1 oxygen, which is 16, and 1 hydrogen, which is 1, and this one gives us 40. Okay, so 40 grams is the weight of 1 sodium hydroxide molecule. Let me call it like that. So 2 moles of that should be equal to 80 grams. I have to multiply just the same way I did there. I say 1 mole of sodium hydroxide is 40 grams. What about 2 mole? The one I want from my chemical reaction there is equals to X. This one will give me 80 grams. At the end of the day, you'll see it's 40 times 2, which is equals to 80 grams there. And then this one must produce for me 1 mole of hydrogen gas. 1 mole of hydrogen gas. I know hydrogen gas is written as H2. Sorry, the work looks poor, not arranged. So it is 1 multiplied by 2 because there are 2 hydrogens and each of them has a mass of 1. So this is equals to 2 grams. All right. Okay. And you see something interesting. If I add this plus this grams, it becomes 82 grams. If I add 46 plus 36, 46 plus 36, this one should be equal to 82 grams. And that way we know that our equation is pretty okay. So if we know what this one tells me that, let me clean up so that we start like a little bit all over again. Okay. With rewriting the same equation just there, it's sodium plus water gives me sodium hydroxide plus hydrogen gas. Balancing it, I think we said 2 there, and 2 there, and 2 there. Let's see, 2 nitrogen, 2 nitrogen, 4 hydrogen, 4 hydrogen, 2 oxygen, 2 oxygen. So it is balanced. I leave the state symbols alone. So I'm saying this one, they are combining in 2 mole of sodium combines with the 2 mole of water molecule to give 2 mole of sodium hydroxide and 1 mole of hydrogen gas. All right. The implication is this. If I tell you that this in this equation, I used 11.5 grams of sodium, and it is a complete reaction, I'm able to check out what was each of the other component that was produced or used. So I'm saying, suppose instead of having 23 grams of or 46 grams of sodium, I had something like 11.5 grams of sodium to react. That's all I had. I had only 11.5 grams of sodium. I want to know how much, how many grams of water I used, how many grams of sodium hydroxide I produced, how many grams of hydrogen I produced. Okay, so I started by finding for myself what is the mass of, what is the moles of sodium do I have? I know that. Sorry. Uh, water, I know that 1 mole of sodium is equals to 23 grams. So 11.5 grams is equals to how many moles? I will do that and you see it ends up that my X is equals to 11.5 over 23 moles. Okay, this one I think once you divide it, you'll find it becomes 0.5. 0.5 moles. All right, and which is what I wanted. So now 0.5 moles of sodium, this is what I have, and I want to pick I'm here at home, this guy. I want to pick yeah. So I know that I have only 11.5 grams of sodium. I have 11.5 grams of sodium, and that is equivalent to 0.5 moles. So this one tells me that if, because now I no longer have 2 moles, I have 0.5 moles of sodium, it must produce, if 2 moles produce 2 moles of, if 2 moles of sodium needed 2 moles of water, then 0.5 moles of sodium will need 0.5 mole of water and will produce 0.5 mole of sodium hydroxide. You see the ratio is like 1:1. Two moles gives you 2 moles. 2 moles reacts with 2 moles, gives you 2 moles. So it means half a mole will react with half a mole to give half a mole of sodium hydroxide. But what about relationship with the sodium? I mean with the hydrogen produced. If 2 moles produce 1 mole, if 2 moles produce 1 mole, I divided 2 by 1 by 2 to get 1. Then I will need to divide this one by 2 to get the number of moles here, and it will be 0.5 over 2, which is 0.25. I'm saying, what do I do to this to get this? I say this to get this, I divide it by 2. Divided this one by 2, I get this one. So I divided this one by 2, I'll get this one there. Okay. Right. So I know that in my equation, I'll react, in my reaction will consume 0.5 moles of water and it will produce 0.5 moles of sodium hydroxide and it will produce 0.025 moles of hydrogen gas, which tells me how much water, how many grams of water am I going to produce. Let me pick a red pen. Considering water, water, I know that 1 mole of water molecule is equals to what we said, 16 plus 2, 18 grams. So 0.5 moles. 0.5 moles will be weighing how will be how heavy, and this one will be 0.5 multiplied by 18, which will give you 9 grams. So we'll use 9 grams of water. Remember, we have said we have used 11.5 grams of sodium. So what is the mass of sodium hydroxide am I going to form? I am saying this, that I know I'm forming 0.5 mole of sodium hydroxide, which must be equal to X gram. But I know that 1 mole of sodium hydroxide is equals to what? We say this sodium 23 plus oxygen 16 plus hydrogen 140 equals to 40 grams. So my mass, my X will be equal to 40 multiplied by 0.5, which will be like 20 grams. 20 square. Okay. And then how much hydrogen will be produced in terms of weight? I know that 1 mole of hydrogen is equals to 2 grams, but this time we are producing 0.25 mole of hydrogen. How heavy is it? And this one will get our X is equals to 2 multiplied by 0.25, and this one will be like 0.5 grams. So you see basic arithmetic, ignore the decimal, do the multiplication, you get the answer becomes 50. Then put your 2 decimal places. Whole number decimal is usually there, 1, 2, so 0.5 grams. So we'll produce 0.5 grams of hydrogen gas. I hope this makes sense. Okay. So if we know the mole of reactants, we can and the product, we are able to come up with what went on in the chemical reaction, and get whatever masses or whatever quantities which is required. Consider a similar reaction, but this time let's react calcium with water. Calcium, sorry, calcium. Our calcium reacts with water to form calcium hydroxide in such a manner, and a hydrogen gas. Okay, so again, the state symbols important: solid, liquid, aqueous, and gas. Then next, balancing this equation. Calcium on the left, one calcium on the left, one calcium on the right. That seems okay. 2 hydrogens on the left, 4 hydrogens on the right. Those are not balanced, so we need to add a 2 there. So we have now 4 hydro 2 H by 2. The whatever is inside the bracket is whatever is outside of the bracket multiplies both of them. So 2 hydrogens plus 2 hydrogens, those are 4. These are 4. Then 2 oxygens there, and 2 oxygens there. And then I think the equation is balanced. So this one tells me that 1 mole of calcium reacts with 2 moles of water to give 1 mole of calcium hydroxide and 1 mole of hydrogen gas. All right. So again, the implication is just as we said. Suppose I tell you that 20 grams of hydrogen gas was produced in this reaction. In this reaction, 20 grams of hydrogen was produced. 20 grams of hydrogen gas was produced. Okay, and note this volume you can be given in gas form. You can be told something like 200 centimeter cubed or 3,000 centimeter cubed was produced. So you need to relate it to the earlier topic. So, but in this case, I'm just saying that 20 grams of hydrogen gas was produced. How much calcium was used in this chemical reaction if the chemical reaction went to completion? So, if that's the case, I'll come here and find out if I am producing 20 grams of hydrogen, how many moles of hydrogen are these? I started by first of all finding the mass of the moles of hydrogen gas I'm dealing with. So I know that 1 mole of hydrogen gas is equal to what? 2 grams. Okay, 1 mole of hydrogen gas is equal to 2 grams. What about 20 grams? 20 grams must be equal to x. So I do my cross multiplication simply, and I'll get my 2x is equal to 20, and then divide by 2, and I'll find that I'm dealing with 10 moles of hydrogen. So I'm saying here that in my chemical equation, my 20 grams of hydrogen is equivalent to 20 moles of hydrogen being produced. If 20 moles of hydrogen was produced, it implies that also 10 moles of calcium hydroxide was produced. It implies also that 20 moles of water molecules was consumed during the chemical reaction. It implies that 10 moles of calcium must have been used. Why? Because we said in these chemical reactions, when they are taking place, they take place using those constant moles. So if you know the mass of one, you know the implication of the other. So I started by first of all being told that 20 grams of hydrogen was produced, and I'm saying if at all 20 grams of hydrogen was produced, which from my calculation shows me that it's equal to 20 moles, it implies that if 1 mole of calcium, or if my normal chemical reaction, once I do it or once I carry it out, it gives me 1 mole of hydrogen. Then if in this particular instance I produce 10 moles of calcium, it means of hydrogen gas, sorry, it means that I must have reacted, I must also produced 10 moles of calcium hydroxide. I must have produced, I'm essentially multiplying each of these molar quantities, molar ratios by 10. So I multiplied this one by 10, I multiplied this one by 10, I multiplied these two by 10, I multiplied this one by 10. So it's everything times 10 times 10 times 10, and here it's also times 10 because I got this times 10, this divided by this, my 10 more divided by this is, I know that this is the times 10 I used to get 10. So that's the general equation. So if I reacted 10 moles of calcium, now I am able to find the mass of sodium I used, not sodium, but calcium I used, because I know that 1 mole of calcium is equivalent to 40 grams. So if I'm dealing with 10 moles, how many grams is it? Is equal to, my X will be equal to 400 grams. Okay, so in this equation, I must have used 400 grams of calcium. Okay, I can go further, look at how much water was used, because I know that 1 mole of water, I think I can calculate down here. In a different pen for correct purposes. I know that 1 mole of water is equals to 18 grams. We said that H2O, H2O, 1O is 16, 2H is 2H is 2, so 18, 16 plus 2 is 18. So 10 mole of water, what is the weight? it will be you cross multiply and you get your x is 180 grams. So it means that we must use 180 grams of water in the reaction. Then I want to know how much calcium hydroxide I produce. Okay, so I need first of all to find the relative formula mass for calcium hydroxide. It's 1 calcium plus 2 oxygens plus 2 hydrogens. Okay, 1 calcium, 2 oxygens, 2 hydrogens. 1 calcium is 40, 2 hydrogens is 2 multiplied by 16, and 2 hydrogens is 2 multiplied by 1. So it's little. Yeah, I'm using the formula is 140 plus the 2 plus 2. This is 4. This is 74. We check that one. 72 plus 2, 74. Okay, so if I'm using if one more, so here we are saying one more, or is it what is the definition? Yeah. If one more is equals to 74 grams, 10 more will be equal to what? 740 grams. 740 grams. Okay. Okay. So that's okay. That's okay. So 740 grams. Okay, and you remember here, of course, in our equation, we started with 20 grams. This is what told us. And then the next question is, you remember, if we add these two, this gives us 760 grams. 740 plus 60 is 760 grams. 400 plus 180, it's 500 and something, so which implies a problem somewhere there. And if you look here, we had a problem somewhere here. We said 1 mole of water is 18 grams. We said that what about 10 moles? But if you remember, we were considering 20 moles of water instead of 2, or instead of 10. So we are supposed to look for 2, which is supposed to give us 360 grams. So here we are looking at 360 grams of water. And if you add them up, this one also will give you 760 grams. Always the left-hand side, the right-hand side tends to balance if all the everything is there. Okay, all right. And that is implied, or such a kind of equation, it will always come in your particular exams. It can change here and there. I want to change a bit, um, or let me just use a different one, and then we'll see what the implication is like. Consider a reaction between magnesium and sulfuric acid. Consider reaction between magnesium and some dilute sulfuric acid, which goes like, sorry, I will get a pen here. Magnesium will react with dilute sulfuric acid. You don't want to use concentrated sulfuric acid to give magnesium sulfate, some sulfate, of course, and some hydrogen gas, like that. So, so magnesium, which is a solid, reacts with sulfuric acid, which is an aqueous solution, to give an aqueous solution of magnesium sulfate and hydrogen gas in gas form like that. Those are the state symbols. Try and see if this thing is balanced. So it is 1 magnesium on the left hand side, 1 magnesium on the left, 1 magnesium on the right hand side, 2 hydrogens there, 2 hydrogens there, sulfate ion there, 1 or 1 sulfur, one S, and four oxygens. Yeah, this is pretty okay because magnesium has a valency of 2, sulfate ion has a valency of 2, they cancel. So this is the correct formula. So this one tells me that one mole of magnesium will react with 1 mole of sulfuric acid to give 1 mole of magnesium sulfate and 1 mole of hydrogen gas. Okay, and we have already pushed in the state symbols. So this one is pretty straightforward because I think the ratio are 1 to 1. We need the one which has a bit of confusion or can bring about some bit of confusion. Let's consider calcium carbonate. Consider calcium carbonate reacting with, let's say, hydrochloride solution or hydrochloric acid to give some calcium chloride and some carbon dioxide gas and some water in such a way, right? Then we try and balance this one. So calcium carbonate is some kind of solid or powder. Hydrochloric acid is in aqueous form. Calcium chloride is in aqueous, is dissolved in water. Uh, the whatever will come as a gas, and the water will of course be, will be in a liquid state, and it will be in a liquid form. Okay, so let's try to balance this one. One calcium on the left hand side, one calcium on the right hand side. Carbon, one carbon on the left hand side, uh, carbon on the right hand side. Oxygen, 3 oxygen on the left hand side, 3 oxygens on the right hand side, 2 plus 1 plus 3. Hydrogen, 1 hydrogen on the left hand side, 2 on the right hand side. So we need to try and make these ones too. So 2 hydrogen here, 2 hydrogen here. What about chlorines? 2 chlorines on the left, 2 chlorines on the left. And I think it is pretty balanced. You can go through it again. So it is important when you're dealing with these equations or in this kind of equation to make sure that it is correctly balanced, because that balancing makes sure that you have the correct mole ratios or molar ratios. Otherwise, now things comes messed up. So again, trying to look at it: one calcium, one carbon, one carbon, 3 oxygens, 2 oxygens there, and 1 oxygen there. Okay, two oxygen there and 1 oxygen there. Then 2 hydrogen, 2 hydrogens, and 2 calciums. I mean chlorines and 2 chlorines. So it is balanced. So this one tells me that one mole, 1 mole of calcium carbonates reacts with 2 moles of HCl and to give 1 mole of calcium chloride and 1 mole of carbon dioxide gas and 1 mole of water molecules. Suppose 88 grams of 88 grams of carbon dioxide was given out. What's the mass of calcium carbonate powder that was used? Suppose here we got 88 grams of calcium of oxygen gas. So I'm trying to pick a different pen. Red pen. Okay, so we are saying 88 grams, 88 grams of CO2 was given out. So I need first of all to find out the moles of contained in 88 grams, because I'm working with moles ratios here. So carbon is carbon, 1 carbon plus 2 oxygens, oxygen by 2. So carbon is 12 plus oxygen is 16, but not 2. This is 12 plus that 2, which is equals to 44 grams. So if 1 mole of carbon dioxide is equals to 44 grams, 88 grams must be equal to how many moles? You see this equals to 2 moles. That is x dot 44 is equals to 88 divided by 44 divided by 44. We have seen this one previously. This one is equals to 2 moles. So I produced 2 moles of hydrogen, I mean carbon dioxide gas, and that's what I'm going to come and do here, 2 moles. So what I did, this one, it was multiplied by 2, or this divided by series is 2. So for each quantity, I need to multiply by 2. So I get 2 moles of water. I multiply by 2. I get 2 moles of calcium chloride. I multiply by 2. I get 4 moles of hydrochloric acid. I multiply by 2. I get 2 moles of calcium carbonate. So if I want to know the amount of calcium carbonate which I was reacted in that chemical reaction, I have to do what? I have to come here and say that calcium carbonate is made up of calcium plus a carbon plus 3 oxygens. Okay, so calcium is 40, carbon is 12, carbon oxygen is 16. So this is 52 plus 48. Is that right? Calcium is 40, carbon is 12, for 3 by oxygen 48. That is 100 grams. 100 grams. So if 1 mole is equals to 100 grams, 2 moles will be equals to x, and if you do your calculation you will find that it will be equal to 200 grams. So you have to react 200 grams if at all you are going to evolve 88 grams of carbon dioxide, right? So and going by that you're able to do quite a number of quite a number of items. Consider this other nice one whereby we use some carbon compound. We can use either carbon or we use carbon monoxide gas to oxidize or to reduce copper oxide to copper to pure copper. That's what maybe we use in copper better. But most of the time, I think you can burn copper in excess carbon, but that one will be on the other side. For now, I want to consider that I have this kind of arrangement to consider. You can do this kind of an experiment, sorry. Okay, so let's say that what diagram that will work. I can put some copper oxide here, copper oxide powder. This is copper oxide powder, and I push in carbon monoxide gas. CO gas. This is a poisonous gas, by the way. This is the gas which is produced if you have if you have your bowler or your charcoal burner, that's why you are told it shouldn't, especially when you are lighting a tap, it shouldn't be, and even when you are using it, shouldn't be in an enclosed room because when you have charcoal is basically carbon. Charcoal is carbon. Charcoal is usually carbon. Your charcoal that goes black, whatever for lighting. the carbon. So when you are burning, when it starts burning, it produces both carbon dioxide and another gas called CO. This carbon monoxide is produced because of incomplete combustion of the charcoal. So because of that lack of enough oxygen, some carbon monoxide is produced. This gas is a bad one. It shouldn't be emitted in an enclosed room. It's kind of a poisonous gas. In your biology class, you are told when the body is transporting oxygen, you have your red blood cells which transport oxygen. So what happens is that when this blood cell is transporting the blood, the carbon dioxide and the oxygen will bind or will be bound onto the red blood cell. It will be taken to the body. Once it goes to the final place where it is being taken, maybe it's in the leg, the oxygen is released into the blood or into the tissue, and from the oxygen, carbon dioxide which was there is taken by the same red blood cell. So releasing of oxygen and picking of the carbon dioxide is easy. Again, so the red blood cell travels again, goes to the lungs. Once it reaches the lung, what it does is to release the carbon dioxide, which you breathe out, it releases very easily. And the molecule is again free to take some oxygen and take it back to the leg or wherever it is needed. Now, the problem with carbon monoxide is that it binds in your lungs. Once you breathe it, it binds with the oxygen, with the red blood cell, but it is not needed in the body because it's useless, and then it doesn't unbind, it doesn't release the oxygen. So with the time, what you have is that you have all your red blood cell, they are bound, and being bound means that they cannot carry any oxygen because they are bound, they are carrying something. The red blood cell can either be carrying oxygen or it is carrying carbon dioxide. So when it goes to the lung, it releases the carbon dioxide into the lungs and picks up oxygen. Once it goes to the body tissue where it is taking the oxygen, it releases the oxygen there and picks up the carbon dioxide. So the carbon dioxide and the oxygen easily bind with the red blood cell and easily unbind. The carbon monoxide does not unbind. So sooner or later, all your red blood cells are bound. And once they are bound, means that there is no one to transport oxygen, there is no one to transport carbon monoxide, and that way you say someone is suffocating, dead sooner or later, because body cannot exist without getting in oxygen to the tissues. Similarly, it cannot exist with all the carbon dioxide being produced in the tissues, but that's biology. If you want more of it, check out our more of our courses in the biology courses in the SmartMe website and there. So what I was saying is that this 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 solution, this carbon monoxide is passed over heated. This you apply heat, you heat this copper oxide, you hit it. Once it is heated and you pass this one, you find this guy, as it is passing, it will pick the oxygen from the copper, and this is called a reduction reaction, and carbon dioxide is produced on this end. Okay, and at the end of the day, you started with some compound which is copper oxide. At the end of it, you find you have some shiny brown compound which is pure copper, right? So the chemical reaction for that also activity is copper oxide reacting with copper oxide to give copper in the pure form plus carbon dioxide. Okay, is this equation balanced? I think it is already balanced. One copper, one carbon, two oxygens tells us that 1 mole of copper oxide reacts with 1 mole of carbon monoxide to produce 1 mole of uh, copper, copper granules, the pure copper metal, and 1 mole of carbon dioxide. State symbols, this is a solid, this is a gas, this is a solid, this is a gas. Okay, so state symbols and balance the equations, very important. So if I know that I produce, let's say, I know I like working to avoid confusion. I just work with a simple volumes. If I know that I produced, I'm trying to find the relative for the mass of copper. Copper is Cu is 64. Yeah, it's your copper. So if let's say if I know that I produced 128 grams of copper, 128 grams of copper, how much carbon dioxide did I produce? How much copper oxide did I start with? So I know that 128 grams. I can take out the left hand side is not important. We have understood what was happening. That I have the working area. Sorry. Pick up pen. Okay. So I'm saying that I know that 1 mole. Oh, I think I picked up pen. I know that 1 mole of copper is equals to 64 grams. So what about 128 grams is equals to X? So I'll find that my X dot 64 is equals to 128 grams divided by 64 divided by 64. And this one will give me 2 moles. So I'm dealing with 2 moles of copper. So here I am saying 128 grams is equal to 2 moles of copper. So this one I multiplied by 2 for me to get that. It means that going by this ratio, I have to produce 2 moles of carbon dioxide. I have to use 2 moles of carbon monoxide. I have to use 2 moles of copper oxide. Okay. So if I wanted to know how much, let's say, copper oxide that I had in the beginning, if I produce 128 grams of copper, it means that I first of all I find the relative formula mass for copper oxide. For copper oxide is equals to 1 copper 64 plus 1 oxygen, which is 16, which gives me what? 0. 8 grams, and that is the mole. So if 1 mole of copper oxide is equals to 80 grams, 2 moles of water of copper will be equals to 80 times 2, which will be 160 grams. So I'll have to have used 160 grams of copper oxide. That's what I started with. Then how much how much how much carbon dioxide did I produce? How much carbon did I produce? I produced 2 moles of carbon dioxide. But we know previously carbon dioxide is 44 grams. We said it's 1 carbon 12 plus 2 oxygens, which is 32. So 44 grams. So if 1 mole of carbon dioxide is 44 grams, 2 moles is equal to X. You do some cross multiplication, you find at the end of the day, you end up with 88 grams. So I'll produce 88 grams of carbon dioxide. Then lastly, how much carbon monoxide am I going to be using in the same chemical reaction? Carbon monoxide, it's in that ratio, 1 carbon is 12 plus 1 oxygen, which is 16. And this one gives me what is it 28 grams. So so if 1 mole is equals to 28, What about 2 more is equals to what? X. You do some your cross multiplication, you find your X will end up to be 56 grams. So here I must subtract 56 grams of that compound. So this one tells me that I have to react 160 grams of copper oxide with 56 grams of carbon monoxide. Remember, this copper oxide is heated up, and that will give me 128 grams of pure copper and 88 grams of carbon dioxide gas. Okay, so I think that is pretty good enough for that particular lesson. We'll continue with the next lesson where we'll be looking at what happens when you are reacting the volumes of gases, and as well as when you are limiting some of the reactants, so that instead of having enough oxygen, you have not enough oxygen. Instead of having enough copper to take part in the chemical reaction, you have insufficient copper, and then we'll see what happens. But that one will be in the next lesson. Very much. Best luck. As I said, once you have gone through this, going through it is the first step. Doing a lot of the exercise is the main deal. So in this journey, there's one way to fly this thing, and the one way to fly it is to do the exercises. Okay. Best luck. See you next time.